now that we know that the coefficients of a convergent power series are actually the derivatives of a certain function, the power series itself, evaluated at our centered value, A, there's a special name for this kind of power series, now that I know what those coefficients are. This is called a Taylor series. It's named after a mathematician who worked with these things a couple hundred years ago. So a Taylor series is just a power series, right? Just some bunches of x minus a raised to some power. But I know that the coefficients of this power series are derivatives divided by factorial numbers. The 0th derivative divided by 0 factorial. The first derivative divided by 1 factorial. The second derivative divided by 2 factorial, and so on. It's a very simple rule for my coefficients. So the full name of this would be the Taylor series of f at coordinate A. Or sometimes you'd say it's about A, or sometimes you'd say it's centered at A. But the A is this really important number right here. This power series will only converge in some interval with A dead center in the middle of that interval. Right? Maybe I have the whole real number line. Maybe I have a finite interval. Maybe I have convergence just at that one point. Now, it's very convenient, as long as our series converge, to take A equals 0. It makes the mathematics a little bit easier to look at. I don't have to worry about subtraction as much. And you'll sometimes see this kind of a power series. It is a Taylor series. You'll sometimes see it given a special name just because it comes up a lot. So if we center the power series at x equals 0, then all of my x minus zeros to the n power, just the same thing as x to the n power, and we'd call this a Maclaurin series. Again, this is named after some long dead mathematician who worked with these things. So Maclaurin series is a kind of Taylor series. Those are the Taylor series centered at x equals 0. Now, these are very useful things if you have a function which is equal to a power series. And that is a very big if. We have seen some functions which are equal to a power series. So in my previous lectures, I've talked about the geometric series, which converges to this rational function. So when I say that 1 over 1 minus x is equal to an infinite sum, n starts at 0 and goes to infinity, and what do I have here but x, excuse me, to the power n? This is telling me two different formulas for the very same function. And these will be equal to each other as long as the absolute value of x is less than 1. Now that I know that this is actually a Taylor series, in fact, this is a Maclaurin series because it's centered at 0. I know that the coefficients here, my coefficient on x to the power n, is supposed to be n factorial on my denominator and a numerator of the nth derivative of my function evaluated at 0. I know that all the coefficients in this power series are just 1. What new information does that tell me? Well, if those things need to be equal to each other, then it must be, I'm a little short on room here, it must be that the nth derivative of my function evaluated at 0 is equal to n factorial. That's the only way that Taylor series makes sense. So if someone walks up to you on the street and they say, quick, tell me the derivative of 1 over 1 minus x, and tell it to me when x equals 0. Now we know. No matter how many derivatives we've taken here, maybe we've taken one derivative, maybe we've taken 101 of them. That's going to be n factorial every single time.